Hello, hello, hello. I'm going to work out the solution to the problem where we have a square, a perfect square with a uniform charge distribution, and the total charge on the square is Q, 2 microcoulomb. The question is, what is the electric field due to this configuration at the center? Let's assume that the square is in a horizontal plane. This is then a vertical to this plane, going through the center, and I call that the y direction. And I also asked you what is the electric field at point P, and P is 0.8 meters above point C. I will leave you alone to conclude before you do any math that the electric field at point C must be 0. If you have any problems with that, watch my solution to the previous problem where we had a ring. I will also leave you alone with the idea that at point P, the vectorial sum of all electric fields will have no component in the horizontal plane. Whatever component in the horizontal plane due to this wire will be cancelled out by this one, and whatever horizontal component due to this wire will be cancelled out with this one. So I will not discuss that any further. I'm only going to concentrate on electric field in this direction. Obviously it is upwards because the charge is positive. I'm going to introduce D, which goes from the middle of this section to point P. Easy to calculate, D, 0.943 meters. So I'm now going to lift out only one wire, and I'm going to calculate what the electric field is of that one wire at point P. And of course, what I will have to do later, since there are 4 wires, if I manage to get the contribution in this direction, I have to multiply them by 4. So I start simple. Here is one wire length capital L, which is 1 meter. The middle of that I call x equals 0. And I slice out at location x an extremely small section dx. And I'm going to calculate at point P, which is in this direction. Here is D, that's D. What is the electric field at point P due to this little bit of charge? How much charge is there here? Well, the total charge on length L is Q divided by 4, and so the amount of charge on this little section is dx divided by L times Q divided by 4. And so this vector that you see here, due to this little charge here, is Q divided by 4 divided by L, famous 4 pi epsilon 0, times this distance square. And this distance square is x squared plus d squared, x squared plus d squared. So that is this component. However, as you will see later why I do that, I really want to know the component of this vector which is perpendicular to the wire. And I call that E, and I gave that this arrow, that means it's in this direction. So to go from this one to this one, I have to multiply by the cosine of alpha. And the cosine of alpha is D divided by the square root of d squared plus x squared. So here is that cosine of alpha. And so I substitute the cosine of alpha in here. And now I have to do an integral from x equals minus L over 2 to plus L over 2. So then I have the contribution at point P of the entire wire. So you see, you have again the Q for L, 4 pi epsilon 0. You have the d of the cosine here. And now I have to do an integral of dx of x squared plus d squared. Now it's to the power 3/2, because this one is multiplied by this one, so that gives me the power 3/2. I solved that integral. It's not very hard. If you have any problems with it, just ask Wolfram what the solution is to that integral. It's perfectly okay. That's not cheating. But I didn't have to cheat. So I give you here that the integral from minus L over 2 to plus L over 2 of dx divided by x squared plus d squared to the power 3/2 is this value. And I have to take that between minus L over 2 and plus L over 2. And when I do that, so I substitute this L over 2 in x here and x squared here, and I subtract this L over 2 here and square there. And so that gives me then an L upstairs, and downstairs I get d squared, this d squared, I get here L squared over 4 plus d squared, and here is my L 4 pi epsilon 0 mu times 4, which is this value 4. Sorry that I wrote it down in a strange sequence, because when I solved it I forgot the pi, and so I put the pi at the end. So this now is the E vector in this direction due to this entire bar. So this is that entire bar, and this E vector is now this vector, because that is the component perpendicular to the wire, and this is that component perpendicular to the wire. So this vector here is this vector there. How now can I get the component that I am really interested in, which is the component in this direction? That's the only one that will be non-zero. I now have to multiply this result by the cosine of this angle, and that gives me then the vertical component vertical to this plane. The cosine of that angle beta is y over d, and here, ta-da-da-da, is my final result. The final result, because I have already multiplied the whole thing by 4. So this 16 becomes simply a 4, because there are 4 wires. And all 4 wires will of course have exactly the same component in this direction. So this is the final answer. Before you go ahead, to make sure that there is not an obvious mistake, convince yourself that this is dimensionally correct. What is required, that the dimension of length in terms of meters has to be 1 over meter square. Just think about that. Go to a point charge and calculate the electric field at a certain distance. You will always see it's divided by a meter square, distance squared. Well, this is in meters. This is in meters squared. So that is 1 divided by meters. And this unit is also meters. So indeed, if we take the length components here, they have the dimension 1 over meter squared. If you have that, it doesn't mean that your answer is correct. If you don't have that, your answer is wrong. So it's a convenient check. So now all I have to do is substitute in here. First of all, if I put in y equals 0, do you see that E is 0? That's what I predicted. So now we will get the final answer. So I use this result and I substitute in there that d squared is this value. I know what y is. Y is 0.8. I know what L is 1. And what do I find? I find obviously at y equals 0, E equals 0, that was obvious. I now find that at 0.8 meters at the center, vertically up, is 1.514 times 10 to the 4th volts per meter. And this, as I predicted, is smaller than the 1.71 times 10 to the 4th in case of a ring. The ring had a radius of 0.5 meters. And this is also 0.5 meters. But as I explained earlier in the problem, you still expect at point P for the square a lower value than for the ring. Because on average, the distance from the locations on the wire to P will be larger than in the case of the ring. And indeed, you see, it's not very much smaller, but it's clearly smaller. Alright, this problem is a classic one. It's not an easy one, because those of you who have no reasonable background in math, they will obviously be totally lost. Notice that the technique that I followed, that I first worked only with one, if I call that one wire. I did all my homework on one wire, and then at the very last I put all 4 wires together. Okay? I fear that the number of correct answers will be small. But that's okay. It happens occasionally. And if you can't do this problem, we'll still be friends, of course, that goes without saying. I'd like to add something to my solution. I did something similar at the end of the previous problem with the charged ring. So for the charged square, this is then the total field, the vectorial sum of the contributions of the entire square. And that E field that I have, that net E field, must be in this direction, simply for reasons of symmetry. Now, I substituted in here that d squared is y squared plus 1/4 L squared. And so you see that there. It's the same equation, but now I have eliminated d, and I have it exclusively in terms of y. Now look at this function, y divided by this. Y divided by y squared plus L squared over 4, and L is 1, times y squared L squared over 2 to the power half, and L is 1. This function is 0, at y is 0. It better be. For y equals infinity, it better also be 0. Because clearly the electric field, if you're infinitely far away from the square, has to be 0. And indeed, that's clear. If you put in y infinity, this is 0, and y is 0. It's also 0. So therefore, as I also argued in case of the circular ring, there must be a point between 0 and infinity where the E field is a maximum. And so that will be the case when this function is a maximum. I did the same thing that I did last time. I asked Wolfram to plot that curve for me. And the curve that you get is very similar to one that we had before, except that the numbers are different. But again, you will see that at y equals 0, it goes through 0, and at y equals infinity, it goes back to 0, and somewhere here there is a maximum. But since the geometry is different for the squares, it's a different curve. But it looks very similar on Wolfram. I just want you to see the shape again. Don't look at the numbers, but keep the shape in mind. So if now I put in y equals 0.8, I find this value for z. But if now I try to get very close to the top of that curve in Wolfram, it's very close to y is 0.39 meters. And indeed z is higher. And you may want to manipulate this to get another digit here, but that's not very important for me. So this is not an exact analytical solution. It's Walter Lewin eyeballing where the maximum is. And so therefore the E field is now higher than at 0.8. And how much higher is it? Well, 1.20 divided by 0.8419 times our famous result that we already found, which is 1.514 times 10 to the 4th volts per meter. And so the highest electric field then would be very close to 2.16 times 10 to the 4th volts per meter. Okay, I think we've beaten this problem now to death. I admit that it's a lot of math, but keep in mind, math is the language of physics. So, if you can't do a problem like this, don't feel bad, but you may have to brush up on your math, maybe rather than on your physics. For those of you who are still a little bit lost, I propose you watch these solutions again. And maybe you also want to watch again first the solution of the ring problem, and then the solution of the square problem. The physics is basically the same in both cases. However, the math in the case of the square is a little bit more complicated. Alright, have a nice day, take care, and I really hope you still want to be friends with me. I'd like to add something to my solution. Remember, this is the magnitude of the E vector as a function of y, which is the distance to the center of the square. I was lazy I wanted to know where the maximum is, because it's clear if y is 0, E is 0, and if y is infinity, it's also 0. So there has to be a maximum somewhere. And I asked Wolfram to plot that curve for me. Wolfram was plotting this for me. And you see indeed that first the equation, the value goes up, reaches a maximum, and then gradually goes down. And so I eyeballed the curve that I got from Wolfram, and I found that the maximum value for E occurs at roughly 39 centimeters above the surface. So that is quite a bit below the 0.8, the 80 centimeters that the problem is dealing with. However, there are many viewers who were way more courageous than I was, and who actually calculated the derivative, the e dy, and set that equal to 0, and then you find the maximum, of course. And several of you sent me their solution, which is very kind of you. First of all, I'm impressed that many of you went through the trouble of doing that. And now I get, at least 20 correct solutions. I mean, analytical solutions. My solution was not an analytical solution, it was eyeballing. And so the exact solution then is that E is maximum when y is L over 2, L was 1 meter, remember, and then the square root, and under the square root is 1/2 times the square root of 5 minus 1. And that then is 0.393. So 39.3 centimeters above the plane, right through the center, is at a maximum. And when you compare that with my 39 centimeters, not so bad, but they deserve more credit than I do. Okay? So, for the second time then, have a nice day, take care, and surely we are friends. That is a given.